Mastering computer science through algorithmic thinking. Computer science is the backbone of modern technology, shaping everything from artificial intelligence to blockchain networks. At its core, it revolves around problem-solving, logic, and innovation, all critical for programmers and algorithm enthusiasts. Understanding computer science principles empowers developers to create efficient systems, optimize code, and tackle complex challenges. Whether you're preparing for technical interviews or building cutting-edge applications, a solid grasp of CS fundamentals is non-negotiable. The foundation of computer science. At its heart, computer science is the study of computational processes, algorithms, and data representation. It combines theoretical mathematics with practical implementation to solve real-world problems efficiently. This discipline spans diverse fields, including software development, cryptography, robotics, and even bioinformatics. Mastery requires a balance between abstract concepts and hands-on experimentation. Data structures, efficient storage and retrieval of data define the performance of algorithms. Arrays, linked lists, trees, and graphs form the basis of most computational tasks. Algorithms. A well-designed algorithm reduces time complexity and resource usage. Sorting, searching, and graph traversal techniques are fundamental to solving problems systematically. Complexity theory. Understanding Big O notation helps evaluate algorithm efficiency. It distinguishes between acceptable solutions and ones that become impractical at scale. Discrete mathematics, logic gates, set theory, and combinatorics underpin many CS topics. Proofs and Boolean algebra are essential for designing circuits and verifying correctness. Operating systems, managing hardware resources and scheduling tasks ensures smooth execution of programs. Concepts like memory management and concurrency are vital for system-level programming. Leveraging online learning platforms. Online courses offer flexible pathways to learn computer science. Platforms like Coursera, edX, and Udacity provide structured curricula taught by industry experts. Coursera's Introduction to Computer Science course covers Python basics, recursion, and object-oriented programming. It emphasizes hands-on coding exercises to reinforce learning. edX partners with universities worldwide, offering specialized tracks in machine learning, cybersecurity, and cloud computing. Their micro-credentials align with industry standards. Interactive coding challenges. Websites like HackerRank and CodeSignal simulate interview scenarios, helping learners refine their algorithmic thinking under pressure. Open source contributions. Contributing to GitHub repositories provides real-world experience. Reviewing existing codebases teaches best practices and collaboration workflows. The role of textbooks and research papers. Classical textbooks remain invaluable for deep dives into theory. Introduction to Algorithms, CLRS, is a cornerstone text for understanding advanced algorithm design. Research papers published in venues like ACM SIGCOMM or IEEE Transactions reveal cutting-edge developments. Reading them cultivates analytical thinking and exposes readers to novel approaches. Many universities publish free lecture notes online. MIT OpenCourseWare offers materials from renowned professors, covering everything from automata theory to distributed systems. Engaging with academic literature requires patience. Breaking down dense prose into digestible segments ensures comprehension without losing context. Practicing problem-solving techniques. Algorithmic puzzles sharpen logical reasoning. Sites like Project Euler combine math and programming challenges to test creative problem-solving abilities. Solving dynamic programming problems builds intuition for optimizing recursive functions. Classic examples include the knapsack problem and Fibonacci sequence calculations. Greedy versus optimal solutions. Greedy algorithms provide quick answers but may lack optimality. Knowing when to use each approach depends on the problem constraints. Graph-based problems like shortest pathfinding, Dijkstra's algorithm, and minimum spanning tree construction, Kruskal's algorithm, appear frequently in competitive programming. Backtracking, used in constraint satisfaction problems, backtracking explores possible solutions recursively until valid configurations are found. Divide and conquer. Breaking problems into smaller subproblems simplifies computation. Merge sort and binary search exemplify this strategy effectively. Bridging theory and practice. Building personal projects translates abstract concepts into tangible results. Developing a compiler or implementing a neural network reinforces understanding of low-level operations. Reverse engineering open source tools reveals hidden complexities. Studying libraries like TensorFlow or React highlights trade-offs between performance and maintainability. Debugging skills. Proficiency in identifying bugs improves code quality. Tools like GDB and Valgrind assist in diagnosing runtime errors and memory leaks. Profiling code with instruments like perf or Visual VM identifies bottlenecks. Optimizing these areas enhances program efficiency significantly. Version control. Git enables collaborative development and maintains project history. Mastering branches, merges, and pull requests streamlines workflow. Testing frameworks. Writing unit tests ensures reliability. JUnit for Java or PyTest for Python automate verification across various input conditions. Exploring emerging trends. Artificial intelligence and machine learning dominate current research. Neural networks mimic human cognition, enabling breakthroughs in natural language processing and image recognition. Quantum computing redefines computation paradigms. Qubits leverage superposition and entanglement to perform certain calculations exponentially faster than classical computers. Distributed systems, scalable architectures handle massive datasets. Technologies like Apache Kafka and Kubernetes manage fault tolerance and load balancing seamlessly. Blockchain technology, decentralized ledgers secure transactions cryptographically. Smart contracts execute predefined rules autonomously, revolutionizing finance and supply chain management. Edge computing, processing data closer to sources reduces latency. IoT devices benefit immensely from localized decision-making instead of relying solely on centralized servers. The future of programming languages. New languages emerge constantly, addressing gaps left by older counterparts. Rust prioritizes safety by preventing common memory-related bugs inherent in C++. TypeScript adds static typing to JavaScript, improving tooling support for large-scale web applications. Its popularity reflects growing demands for robust front-end frameworks. Functional programming concepts influence mainstream languages. Haskell's pure functions inspire cleaner abstractions in Scala and F#, promoting immutability and concurrency. Domain-specific languages, DSLs, simplify complex tasks. SQL queries databases effortlessly, while regular expressions manipulate textual patterns intuitively. Career opportunities in computer science. Software engineering remains a top choice, involving full-stack development, API creation, and mobile app design. Full-time engineers often work remotely, enjoying global flexibility. Data scientists analyze vast amounts of information using statistical models. They employ Python libraries like Pandas and scikit-learn to derive insights from unstructured data. Cybersecurity professionals protect digital assets against threats. Penetration testing and encryption protocols safeguard sensitive information from malicious actors. Cloud architects design scalable infrastructures leveraging AWS, Azure, or Google Cloud Platform. They optimize costs while ensuring high availability and disaster recovery capabilities. Academic researchers pursue PhDs focusing on AI ethics, formal methods, or parallel computing. Publishing peer-reviewed articles advances scientific knowledge globally. Developing effective study strategies. Active recall outperforms passive reading. Flashcards summarizing key definitions aid retention better than skimming textbook chapters. Spaced repetition schedules review sessions over time intervals. Apps like Anki implement this technique automatically based on difficulty levels. Teaching others, explaining concepts verbally reinforces understanding. Tutoring peers or writing blog posts clarifies ambiguities and strengthens communication skills. Making mistakes. Errors are inevitable during learning phases. Debugging failures fosters resilience and deeper conceptual clarity rather than discouragement. Setting goals. Define measurable milestones like completing specific projects or passing certification exams. Tracking progress motivates continued improvement consistently. Conclusion: computer science is a dynamic field requiring curiosity, perseverance, and adaptability. By combining rigorous study with practical application, professionals continuously evolve alongside technological advancements. To thrive in this domain, embrace lifelong learning. Engage actively with communities, experiment boldly with new technologies, and always seek opportunities to expand your expertise further.